Hello, I'm Andrew Webb, Machine Learning Research and Development Engineer at vTime Limited. This talk is a collection of advice for getting into machine learning or deep learning. We'll cover things like making use of freely available data and state-of-the-art solutions, and how to get ready for your first machine learning project, including the hardware and resources that you'll need. Before we get started, I'll use some of the machine learning technology we've developed at vTime to create a co-presenter for this talk. Using our latest app, vTag, I'll take a photo, and the machine learning backend will generate an avatar based on my face.
Hi, I'm Andrew's avatar. So, Andrew, what is machine learning and what is deep learning?
Well, here are four closely related terms: statistics, machine learning, deep learning, and data science. All of these are about data and learning from data. So what's the difference? Simplifying a little, statistics is about understanding data and forming hypotheses about data, whereas machine learning is much more about making predictions. To give a very simple example, suppose that I'm a bank and I have some data about my customers, their ages and their salaries, and the probability that a customer will default on a loan. In statistics, you'd try to learn something about the actual underlying relationship between these three attributes, and maybe you'd try to say something about how confident you were in your conclusions. In contrast, in machine learning, you'd instead try to predict one of these quantities from the others. A typical picture in this example would be having the age and salary data coming in at the top, this thing in the middle that we call a model, and a prediction for whether the person would default on a loan coming out of the bottom. You can think of a model as a black box with some dials on it, and you set the dials to make the model make correct predictions on the data that you have. This process is called training the model. You don't often care in machine learning if the model is a good description of reality or if it encapsulates the underlying causal relationship between the variables involved. You just hope that it makes good predictions when a new customer comes in asking for a loan. Deep learning is really just a subfield of machine learning. Again, simplifying a little, deep learning is characterized by large models and large input or output data. For example, in deep learning, the input might be an image and the output a prediction of what's in that image. Or the input might be an audio file of somebody speaking and the output a prediction of the transcript, the text of what's being said. And the model in deep learning has many more parameters or dials. In modern state-of-the-art models, there might be billions of parameters. Finally, data science is a multidisciplinary field that can be thought of as an umbrella term for fields related to data. This presentation is about machine learning and deep learning. So to summarize, the task is to use training data to train a model to make predictions on future unseen data.
That's great. So can you give us some examples of machine learning in game development?
The previous example about predicting whether somebody will default on a loan isn't very inspiring. So let's see some examples of how machine learning can and is being used in game development. One example that you may have seen is the OpenAI 5 project, which used machine learning to train a bot to control a team of 5 players for 5-on-5 matches of the game Dota 2. This was very successful, with the bot being able to defeat international champions as of 2018. This was a research project requiring supercomputer resources, but the approach taken was general, not specific to the game in question. It could soon be easier and cheaper to develop game AI in this way, i.e., as actual AI. Machine learning has also been used experimentally for content generation for games, for example, to produce new levels for Super Mario. Natural sounding speech synthesis is now possible with machine learning. Given some text, you can generate speech audio in a variety of natural sounding voices. You could imagine using this technology to create speech audio content for a large number of NPCs in a game without having to hire a large number of voice actors. Another application of machine learning to gaming is super resolution. That is, taking low resolution images and producing plausible high resolution versions of those images. One application of this technology was in a community-produced mod for the PC port of the game Final Fantasy IX, as you can see here. They took every texture in the original game and upsampled them. NVIDIA now has a similar feature, DLSS, standing for Deep Learning Supersampling, which is applied live to upsample frames during gameplay. For example, you can render at 1080p resolution and use DLSS to upsample to 4K, but at a higher frame rate than you would be able to render natively at 4K.
Wow, that sounds promising. So if I want to train my own deep learning models, should I buy hardware or use cloud computing services?
Well, training a deep neural network is computationally intensive, but particularly well suited to GPUs. The thing that really enabled deep learning between 2010 and 2012 was the use of GPUs for training. So, training a modern, large deep neural network requires a high-end GPU, but high-end GPUs are quite expensive. So should you use cloud services or buy your own hardware? And if you do buy your own, which GPUs should you go for? It's hard to do a direct comparison between the cost effectiveness of buying hardware versus using cloud services, partly because there are so many competing cloud services available, and partly because cloud computing providers don't use consumer-grade GPUs, for reasons I'll shortly explain. Having said that, we can make a roughly fair comparison. A single RTX 3090 GPU and a suitable machine to put it in will set you back somewhere between £2,000 and £2,500. Accounting for electricity costs, a roughly comparable GPU instance on Amazon Web Services will cost more than that after 1 or 4 months, depending on whether spot pricing is used. This assumes a 24/7 workload, which may seem unrealistic, but you could easily find yourself training deep neural networks for uninterrupted blocks of time as long as 2 weeks. So, unless you need to occasionally operate at scale for some reason, in which case cloud computing can be useful, for training a deep neural network, you're probably better off using your own hardware. So, which graphics cards are suitable? You might think the answer would be complicated, as there are so many options. But the first thing to note is that NVIDIA really is the only option, as AMD just hasn't put the same resources into developing its hardware or its software for deep learning. Secondly, out of NVIDIA's GeForce, Tesla, and Quadro ranges, the GeForce range, i.e. the consumer-grade gaming cards, win by a mile in terms of value for money for deep learning. The third consideration is GPU memory. Depending on what you're doing, the minimal viable GPU memory will be somewhere between 8 and 10 gigabytes. With all those considerations taken into account, that leaves only 3 GPUs to choose from in the current lineup: the RTX 3070, the 3080, or the 3090, depending on your budget. Note, these have been released in the last few months, so this will be up-to-date information probably until the next GeForce release. Here's a chart of performance per dollar of some current NVIDIA GPUs on a deep learning task. And you can see that there's somewhere around a factor of 4 or 5 difference between the 3 GPUs I've recommended and the others, which are from the Quadro and Tesla ranges. This chart is adapted from timdetmers.com, And incidentally, he has written some very thorough articles on suitable and cost-effective machines for deep learning on his website. Some people are put off using the GeForce range of graphics cards for deep learning for commercial use by the end-user license agreement for the drivers for these cards. The license agreement says that the software is not licensed for data center deployment, but this will not affect you if you're using the graphics cards internally within your company. It does go some way to explain why cloud computing just isn't cost-effective for deep learning. The cloud computing providers cannot use these cheaper cards.
On the topic of being cost-effective, are there any free resources I should be making use of?
One important thing to keep in mind with machine learning is that you don't have to do everything from scratch. Academic research groups will routinely release the code associated with their models, either already trained on some data of their own, or with instructions for how to train the model on your own data. The big tech companies that have large, well-equipped machine learning research groups, so Google, Facebook, Nvidia, and so on, will also release their code and models, though they often do a partial release, keeping the best state-of-the-art models for themselves. Even more valuable, in my view, than models are large, freely available datasets. Deep learning models in particular require a large amount of data to work well, often more data than you could plausibly collect, clean, and annotate yourself. If you have a problem that requires image, video, voice audio, or text data, there's likely a large dataset already available. Here's an example of using some freely available resources. Here we have a research paper about making people look like cartoon characters. Let's say we want to adapt this model to make it turn people into images of dolls. We see at the top of the paper a link to some code on GitHub. The GitHub repository has instructions for training the model on your own data. We Google around and we find a free dataset of human face images and another dataset of doll images. And we follow the instructions in the GitHub repository, and it just works. A day later, we have a model that takes an image of a person and gives you an image of that person if they were a doll. The results aren't perfect, you wouldn't deploy this, but it took very little effort to get to this point. How do you find these freely available models and data without having to trawl through research papers? Well, a good place to start is a YouTube channel called 2-Minute Papers. This channel has videos, usually 5 to 10 minutes long, about exciting new results in deep learning. And where available, it points you to their data and code as well.
Thanks, that's a good tip, I'll check it out. So what should I expect from a deep learning project? And how does it differ from software engineering?
In a software engineering project, you design something and you build it, and if it doesn't work, then it might be a fundamental problem with the design. But it's more likely that you're confident that the design is largely correct and you have 1 or 2 bugs in the implementation. You can test the behavior, maybe you have a unit test suite, and you can determine quite quickly if the thing is working or not. So you've got this quite tight development loop, and every time you fix a bug, you know that you're closer to having a correct implementation. If there's a flaw in the design, it likely takes the form of an edge case that you hadn't considered. That's not a problem, you modified the design to handle the edge case. Let's contrast all of that with deep learning. In deep learning, you collect some data, you design a model, you build it, and you train it. Generally, you can't be confident up front that your design is correct for the problem. The test of success is whether the model makes good predictions on data it wasn't trained on. If it doesn't, you go back to the drawing board with the design or the data collection, either by thinking about the problem or by surveying the research literature to see what other people have tried. This isn't like finding a bug and fixing it. You've no guarantee that the next design will be any better. The development loop isn't as tight. Just retraining the model after a redesign might take a day or a week. Fundamentally, the method of working is much more experimental. The analogy to finding an edge case is finding some data on which the model makes poor predictions. Maybe you can patch that up by collecting more data similar to the problem data to train on. But there will always be more edge cases. When you deploy this model in the real world, there will always be the possibility of some input data that's nothing like anything encountered during training or evaluation, and then all bets are off. You will never be sure that the model will make good predictions on new, unseen data. Another thing to consider with deep learning is that you should nail down your requirements early on in the project, even more so than in a software engineering project. Here's a relevant comic from the webcomic XKCD about the difficulty of telling the difference between a trivial problem and a hard problem in computing. In the comic, somebody is giving requirements to a software developer, and the first requirement is that the user takes a photo and the app should tell them whether or not the photo was taken in a national park. Sure, that'll take a couple of hours, the dev says. The second requirement is that it should check if the photo has a bird in it, and then the dev says, I'll need a research team in 5 years. This comic is now 6 years old, and the problem of determining whether or not a photo has a bird in it is well past being a solved problem. You could probably throw something together to do that in a few hours, including finding the relevant training data. But the point of the comic still stands. There's a fine line, particularly in deep learning, between the kind of problem you can solve in a day and the kind of problem you could solve in 6 months if you had the resources of Google or Facebook. For that reason, you should decide on your requirements up front and resist feature creep. Otherwise, you might find yourself crossing that line. One common and simple reason that one problem can be hard while another similar problem can be easy is that the training data just doesn't exist for some problems. Say you ask your machine learning engineer for the model that can tell you whether an image is of a bird, and they come back a few days later with the model. Then you tell them, actually, I want a model that can tell you which species of bird is in this image. Qualitatively, this isn't really a harder problem, but now you're stuck because nobody has prepared a data set of images of birds annotated by species, and you don't have the resources to do it.
Are there any other gotchas we should be aware of? What about legal and ethical concerns of training our own machine learning models?
First, you should make sure that you're compliant with GDPR or the relevant post-Brexit transition period legislation. For example, the articles considering data purpose limitation and automated decision making. Secondly, there's licensing. As I said earlier in the talk, if you work in machine learning, you will probably make use of models and data produced and prepared by other people and organizations. You should check what licenses these code and data are under. Sometimes they'll be licensed for non-commercial use only, but often you'll be pleasantly surprised to find they're under a permissive license. This is especially true for code and data produced by academic research groups, but it's also often true of work produced by the research and development teams at the big tech companies. There are many ways that a deployed machine learning model can be harmful, and I can't cover them all here. One common problem, though, is bias. Bias in machine learning is most visible when the data is image data. For example, there's a long history of deployed face recognition technologies, for example in camera autofocus technology, that work measurably less well on black faces than on white faces. This is obviously the kind of thing you want to avoid. Why would a model be biased? Well, because it's trained on data, and that data reflects human biases. It's not hard to find examples of this. Possibly the most commonly used dataset of human face images is the Celeb A dataset. This is a collection of 200,000 images of celebrities annotated for attributes like whether the person is wearing glasses or is wearing a hat or has a beard. Here are some example images from the dataset, and the first thing you'll notice is that the images of white faces outnumber other ethnicities. This is because this is true of celebrities in the United States, where the images were prepared. If you dig into the data, though, there are worse problems. One of the attributes in the dataset is attractive, which is supposed to tell you whether the person in the image is attractive or not. This is obviously subjective and obviously potentially problematic. And it turns out there's a strong correlation in that dataset between a person being white and being labelled as attractive. If you train a model on this data, that bias may manifest itself. Here's an example. This is from a paper about a model that takes photos of people and makes them more attractive, like Facetune. But if you look at these three examples, it's made the skin slightly paler in each case. That's a very visible example of bias in data, but you should be aware that bias in data can be much more subtle than this. I'd like to conclude on the point that while it might appear that the large tech companies have cornered the market on deep learning technology, this isn't the case. By building on top of freely available models and data, you can get an application up and running with limited resources, as vTime has been able to do as a small enterprise. Moreover, there are so many potential applications of deep learning and machine learning that the big players can't possibly pursue them all. Thank you for listening.
And thank you to Develop for giving us the opportunity to present this year under these unique circumstances. Goodbye.